Welcome to a lesson with Dr. Powell. This is part two to an example of solving a system of equations. In part one, we found one solution by looking at the reduced row echelon form. Now, in this part, we will find all solutions. So if we find one solution, we can actually vary that one solution by adding to it any vector at all in a particular vector space. We'll think of this vector space as kind of being how everything that we can vary this guy by and still get an output of 26, negative 24, negative 7. In fact, this right here describes the fiber of the function f over this codomain element. All fibers are simply vector shifts of the fiber over 0. Everything that maps to the 0 vector. So this is really, when I say f inverse of 0, I really mean f inverse of the 0 that lives in the codomain. So the additive identity of the codomain. So this is like 0, R3, if you think about it like that. So another way of writing that down is simply a vector of zeros here. So that's what I mean when I say f inverse of 0 right here. So really what we're trying to find then is f inverse of 0. How are we going to find it? Smith normal form will help. So looking at this part right here, we're working our way to the Smith normal form of the matrix function f, and we're getting close. But we need to do some column operations to get here. So think about doing column operations before the matrix function f and doing row operations after in this way and as we compose. We've already done the r here to f, and so we know what this looks like, r of f. That's simply this right here as a matrix function. The Smith normal form, which is everything put together, looks like this. So let's kind of see how this would work. How are we going to find the fiber over 0 of the function f? Well, first, we find the fiber over 0 of the Smith normal form right here. This shouldn't be too bad. We have a column of zeros right here, and we already know, therefore, that this matrix function sends E3 to 0. So E3 is definitely in the fiber over 0 for the Smith normal form. In fact, its whole span is. Any multiple of it will be sent to a multiple of 0. So we're good there. And in general, let's try to think about something like with an x, y, z coming into S. What is S going to do to it? It's going to take the x right here and multiply it to that column, the y multiply it to that column, the z multiply it to this column. The only way to get the 0 vector out of this would be to x and y have to be 0 themselves. Z can be anything it wants. Well, that actually tells us, quite literally, that the fiber over 0 for the Smith normal form is 0, 0, z. Or in other words, z times E3, but z can be anything it wants. So basically all multiples of E3 is just the span of E3. So the span of the span of E3 is going to be the span of E3 is going to be right here, the fiber over 0 of the Smith normal form. Okay, now let's think about this for a minute. The row operations that we do are reversible, and the column operations are also reversible. This is an isomorphism. It's bijective and very nice, and it has a reverse map that preserves structure. Okay, so this tells us something. So that okay, if we have something over here in the span of E3, and we run it through, we'll eventually get to 0, of course, because that's what we just talked about right here. The image at the end will be the 0 vector. So when I write 0 here, I'm really talking about the 0 vector. This is like a 0 of R3 here, but for sake of notation and clarity, we'll just remember that. If we want, we can even write maybe just a 0 little thing here. Remember, it's talking about a vector here. That's a vector. All right, just to kind of keep that clear in mind, what 0 really means in that case, in this notation. Okay, so E3, the span of E3, is sent completely to 0. Now, when we send it over via the column operations map or function, all right, and it outputs something in the domain of f, which is again is R3. And when it comes in here, so everything in here, it has to be sent to 0 eventually. Well, notice that if it's sent to 0 eventually, the only things that R can actually take to 0, because R is an isomorphism, is 0 itself. I mean, this is bijective and injective, and every fiber only has one thing in it. So 0 is the only thing that's sent to 0 to begin with here. So that means that anything in here has to be 0 at this point as we're heading over here. So, which means everything in here is 0 at this point, which means it must have been inside of this fiber. It must be sent to 0 by f. Everything in here, so everything in the span of E3, we take it to the column map or through the column operation, and its image over here. So the image of E3, the span of E3 in this function, we'll call k. All right. Well, and we'll see that it actually is equal to this in a second. So, so basically we have this. We're considering this right here. And we know that everything over here has to be sent to 0. So we know that this is actually contained inside of this, because everything in here has to be sent to 0, right? Okay, now, and it actually turns out that we have equality, meaning we have the opposite inclusion as well. And that opposite inclusion happens because if we assume now that we have something in here, something that's sent to 0. Okay, so this is sent to 0. Remember that C is bijective, and it has an inverse. It's surjective, in fact, which means that anything in here. Okay, so if you take anything that's sent to 0 over here, it actually came from somewhere over here, because everything over here is an image of something over here, which means that, which means since it came from something over here and we run it back through and it get to 0 eventually, which means it must have been in here to begin with. So everything, so what that means is everything in the fiber over 0 actually came from somewhere over here. So we have inclusion going this way. So these two guys are actually equal. So this is nice. We actually have a nice way of computing what the fiber over 0 is of f using, using the column operations matrix. All we got to do is figure out what C sends the span of E3 to. Well, just think about the matrix function C written as a matrix under the column interpretation. E3 comes in, and in this column right here, is going to be the image of E3, and the span of that is going to be precisely what we're after. So we just got to write C down as a matrix. How do we write the column operations as the cumulative, all the column operations as a matrix? Well, we can do that by thinking about what C is. C is the identity composed with C on this side. We could think of it that way. And if we do that, then realize what C is doing if we write it on this side. It's just doing the column operations, the identity matrix. So if we do that, we'll end up getting the column we'll end up getting the matrix for C. So the same column operations that we apply to this reduced row echelon part, we do to ignoring this column, of course, just thinking about the function f, we do to the identity matrix, and we end up getting the matrix for C. Then, after we get the matrix for C, we simply take this column of C, and the span of that is the fiber over 0 of f. So all solutions would simply be 0, 1, -2 plus any vector in this span. In fact, even just take 1, 1, 0, which is in the span, just add those together and see what we get. So if we add them, we'll have 1, 2, and -2. And notice that notice that this is actually, in fact, we can just see quickly that it's a linear transformation, that it works here. And because it works here by isomorphism, it should work up here. So because we have an inverse map going back from here to here, because the row operations were reversible. So if we put a 1 here, so we have, in fact, just think about this. So 1 and then -2. Hey, that's a -1. That worked right there. Okay, and then right here we have 1 times -2. That's -2. It worked. So it did work. So, and that's just one example of this working. But in general, anything at all in this span right here added to this vector will be a solution. Okay, so let's just kind of quickly go through what the column operations were to arrive at C. So from here, notice what's being done. To get to Smith-Noel form, we'd swap these two rows. So we just swap them over here. So we do the same operation. We just swap those guys. That's okay. Hold on. So we swap those guys, and we end up getting also 1, 1, 0, 0. So we swapped them. Then after we swap them, so we're gonna have it's gonna have like a 1 here and a 0 here and a 0 and a -1. And the next thing to do would be to do to an airdrop. This added to that. And that actually gives us that actually would give us the Smith-Noel form that we're after right here. So that one airdrop is what we do right over here. So this column going over to that one. And that's how we get this matrix. And then we just pick out that column, which corresponds to the column of zeros here. And there we go. And then we're done. So we know that all solutions are simply this vector plus anything in this span. Thanks for watching.